All right. So we've been talking about chemical kinetics, right? We've gone through the derivation for simple unimolecular uh, uh, kinetic transition. We've thought about bimolecular transitions. We've talked about what a reversible reaction looks like at equilibrium. And then last time I derived this general case of a unimolecular single step chemical transition or transition, um, uh, assuming reversibility, but not at equilibrium, right? And so in all of these cases, we've been thinking of chemical kinetics. We've been uh, sort of presenting, or I've been presenting this to you as this mathematically rigorous description of this process of converting A into B or A plus B into C or something like that, right? And all the mathematics that goes, simple mathematics goes with that, lets us predict the temporal progression of these transitions as well as those rate constants that describe them. But if you think about it, does any of what we've gone through explain why a given chemical reaction goes as fast as it does, while another one goes slow? There's absolutely nothing in any of that description I've gone through the last couple of lectures that provides a mechanistic explanation for why a given rate constant is large and another rate constant is small, right? It's analogous to the thing we've already talked about when we thought about um, the mechanistic power of, say, the Adair derivation for ligand binding versus the Monod, Weinman, and Changeux, or Cauchy, Matthew Fellmore, or the Perutz model, right? Those other models had mechanistic insight in physically what was going on, whereas the Adair derivation mathematically would fit the data, but it had no physical meaning, right? The description of kinetics we've gone through so far falls into the same category. It's mathematically rigorous, incredibly useful, but like Beer's law, but mechanistically provides no insight into why rate constants have the values that they do. And that's something we want to understand, right? And with everything we've talked about up to this point, the single connection we've got, the explanatory power um, that I've presented to you guys so far for why things happen has to do with energy, right? Specifically, we've been thinking in terms of the Gibbs work function, so Gibbs free energy. But I've also pointed out that knowing the free energy of, say, A and B in a transition like that provides you no insight into how fast it goes, right? Thermodynamics, in terms of just the change of state, provides you no insight into how you get from A to B. It just tells you whether it's possible or not under a given set of conditions, right? But because energy is so useful in these other contexts, our instinct is that energy somehow is connected to this, right? So if we think about, again, this idea of A turning into B, a simple unimolecular process with that rate constant, right? Like I said, our instinct is that somehow the magnitude of that rate constant, right? Why it's as big as it is somehow connected to energy, right? Just sort of instinctively, energy somehow has to come into this, right? The question is how and why, right? Well, another way to think about these these rate constants is as a probability, right? So the higher that rate constant, remember it's in a simple unimolecular process, it's per time, right? So per second or per minute. The larger that value and the nature of those minutes, or the nature of those units in terms of their magnitude, um, would sort of tell you the probability that A is going to turn into B in some arbitrary amount of time. If the rate constant's big and the units are like seconds, right, it's going to happen fast, right? If the rate constant magnitude is much smaller and the units are in hours, it's not going to happen very frequently, right? The probability of the transition is low. So that instinct, right, then leads us to start thinking about what would govern those probabilities, right? Okay. Well, this is not a new question, right? People have been wondering about simple the question like this: Why do reactions go the rate they go? In a quantitative way, what we would think of as like a scientific way since at least the mid 1850s. And the question had been coming up as chemistry was turning into a real science in the early part of the 18th century. So for at least 100 years before that, by about the mid 19th century, people were really trying to dig in with these new tools of science to understand, how this is working, right? And the first person to really approach this question of why reactions go the way they do was a Swedish chemist, famous chemist, of course, by the name of Arrhenius. You may have heard his name before, right? So Arrhenius, make sure I spell his name right. All right. Specifically, his name was Svante. Like I said, he was a Swede. He was following on the work of Van 't Hoff. And he provided the first really quantitative explanation for why reactions might go or could go the way they do, right? Why the reaction rates are proportional to things they're proportional to. And he called this collision theory, right? So to understand how this works, what you have to remember is that the years before and during Arrhenius's time, people knew that there were a couple of things that were really important for specifying reaction rates, right? Of simple chemical reactions. And one of the things you have to remember is Arrhenius and the people working at this early time, we're talking about reaction rates or rates of reactions in the gas phase, right? So that's an important clarification. But people knew these reaction rates were proportional to clearly so if you're imagining a simple reaction like the one I have written up here, this one, right? That reaction rate, assuming it's in the gas phase, people knew it was going to be, say, proportional to the concentration of A, right? Yeah, or so the reactant concentration, for example, right? That's one thing it was going to be proportional to. And the other thing, of course, was temperature. All right. So Arrhenius took some of these ideas and he thought about it, and he did a lot of measurements. And what he showed was something pretty important, which is that for these relatively simple chemical reactions in the gas phase, if you considered the natural log of the rate constant, right? So assuming you're taking these measurements and you can measure these guys, if you consider the natural log of those rate constants and you plot them out versus the temperature, and specifically the inverse of the temperature, what you find is that these, for well-behaved simple chemical reactions, nuts. The rate constant is sort of inversely and linearly related. Let's see if I can draw that a little bit better. Inversely and linearly related to the inverse of the temperature, right? So the log of the rate constant is linearly related to the inverse of the temperature, right? So Arrhenius, looking at that, thinking about it, it's like, well, that's kind of interesting. What is temperature going to be related to if you just think about a simple system, especially in the gas phase, right? What is temperature sort of proportional to, right? In the gas in particular, it's going to be direct proportional to the kinetic energy of the molecules, right? Higher the temperature, the more kinetic energy they've got, the faster, more energetically they're moving around. And he's thinking about that and it's like, well, okay, they're banging into each other. The more energy they got, the harder they're going to bang into each other. So the higher the temperature, the higher the collision energy, right? And if you're thinking about, which the guys often were, reactions that were more like A plus B, right, goes to C, right? It's easier to see how that idea would be super appealing as a way to try and get a chemical reaction going. These two guys have to come together and you have to deform them to make a new reaction happen. The harder they bang into each other, maybe that's connected, right? So Arrhenius, thinking about this, sort of postulated, well, what are the things that are going to matter for a reaction like that? Well, getting a little more quantitative about it, the frequency of the collisions is going to matter, right? How often these guys bang into each other, that's going to be proportional to how fast this reaction goes, right? And then, as we've sort of been postulating or musing over here, how much energy they've got when they whack into each other, or the fraction, right, of the collisions with enough energy is going to matter. All right, relatively simple idea. All right, so you think about that. What's going to govern the collision rate, right? I should say the frequency of collisions at a given temperature. What's going to matter? It's the concentration, right? It's simply the concentration, right? Which means if for a simple chemical reaction like this, what's going to govern the collision rate? It's going to be the frequency with which these guys bang into each other, which is directly proportional to their concentration, and the probability that they whack into each other is just the product of their concentrations, right? So that collision rate, right? Let's write this down here. For that reaction, like I've written it there, the collision rate is just going to be proportional to the concentration of A times the concentration of B that I've got. That's cool. All right, well, that's, fine. We can sort of check that guy off. What about the fraction of collisions with enough energy to carry out a reaction, right? Well, turns out another famous physicist by the name of Boltzmann figured that out for us. The Boltzmann distribution had already been worked out and shown to be related, an exponential function of energy. The energy distribution of molecules in a system like this is an exponential function of some parameters, gas constant, temperature, and specifically the fraction, fraction of molecules with a particular energy, which I'll write down here in a second, is proportional to the exponential of that energy, which we're going to call E sub A, divided by RT, gas constant, right, temperature. So if we put those two ideas together, there's our collision rate, right? And then our fraction of molecules with enough energy, we can now combine those two, right? Because that would mean the overall rate, the velocity of our reaction, would have to be proportional to the collision rate, right? Right, that's our total number of collisions, times the fraction of those collisions that actually are energetic enough to react. Okay, I've dropped a sign here, minus E to the minus E sub A over RT. Oh, that's kind of interesting. Because what that means, right, if I can write this another way, remember, if I wanted to write out the rate sort of equation, right, the overall expression that would describe a process like this, right? If I wrote it out the way I did it before, this velocity of this reaction is going to be equal to K, our rate constant. In this case, it's a bimolecular. K times the concentration of A times the concentration of B. When we look at those two, that means K has to be proportional to E to the minus E sub A over RT. And as we've done several times, we can make that proportionality equal to equality by adding a constant of proportionality. So that means K would just be equal to, symbol Q is often used for this, E to the minus E sub A over RT. Q's our proportionality constant here. It takes care of the units and a bit of a fudge factor, right? But that overall expression now, the amazing thing or really useful thing about this is that has now related what I've described for you up to this point as basically phenomenological numbers that just drop out of the mathematics of describing this process. It is now connected that number, that rate constant, to energy, right? So the size of that rate constant is now directly related to a physical property, the energy of the collision, right? The bigger the the collision energy, right? It's e to the minus, the smaller the rate constant, right? The more energy it takes, the smaller fraction of the population at a given temperature can actually react. And this is great because you do experiments like this, like Arrhenius did, and this works beautifully. I mean, it's totally predictive. It seems really good. This number, sometimes known, well, I should say, the concept here is that we have an energy barrier. Right? For a given rate constant, any collision with enough energy at or in excess of that energy barrier has enough energy to react, right? Any collision with energy below that reaction is not going to react, right? This is also sometimes known as the Arrhenius energy. Right? And one of the reasons I present this is because these plots, kind of like hill plot, or some kind of like plotting the hill equation, right? These are also known as Arrhenius plots. This plot of the natural log of the rate constant with respect to the inverse temperature is an incredibly common, useful tool for sort of, to a first approximation, examining how much energy is necessary to get a reaction to go, and changes in these plots can be diagnostic sometimes. So you see Arrhenius plots a lot, and this is what people are talking about. Okay, so this was great. Collision theory seemed to work really well for lots of these gas phase reactions. There was only one or a couple of problems. As people continued to study chemistry, and particularly started moving out of the gas phase reactions into solution phase reactions and more complex molecules, this collision theory idea didn't seem to always work. In fact, sometimes it failed spectacularly. One of the other things it didn't work for is when people started studying chemical reactions where they could add another substance, and that substance would speed the reaction up but not get modified, what we started, of course, talking about as catalysts. Collision theory can't really explain catalysis very well. And that was a big problem because there are more and more of these catalytic reactions seem to show up, especially when you started looking into biology, biochemistry. Collision theory just became kind of useless for explaining things like that. So there was something missing, right? And that something then came from a next set of developments that we'll take up in the next video.